All right, so the atomic spectrum, or atomic spectra. We could see from that video that light is made up of discrete particles, which we call photons, and each photon has a discrete fixed amount of energy. Okay, and this idea was met with resistance, as most new ideas are, from the scientific community, simply because a couple of hundred years before it had been shown that light behaved as a wave, not as a particle, so they needed new evidence to show that light could behave as a particle as well. And it was the spectral lines of the hydrogen atom and the new model that Niels Bohr came up with that was this new evidence that allowed the dual nature of light to become accepted. So there are two types of spectra. There's the absorption spectra and there's the emission spectra. The absorption spectra is where light is removed from the spectra and you end up with dark patches. So what we see on the screen here is this is the spectrum of visible sunlight, and there are gaps in the spectra where these lines coincide.
How do we get that? That light's coming from us, from like the sun per se, right? And we get our little triangle out, we diffract it, and we see it. Is that what you mean?
Yep. So you put this through a diffraction prism, and you put a screen, and the light goes through the diffraction prism, it diffracts and it spreads out into the spectrum like we've seen in previously. And when you look at the spectrum, there are gaps. Okay. And there are gaps because something has absorbed that energy. Remember that the spectrum is an energy spectrum, and you've got gaps in that spectrum. So there's gaps in the energy levels across the spectrum.
And then like the inverse of that, right, is if we just have that. So say like, okay, this is the light that doesn't get absorbed, and then like there's the inverse where everything else is black and you just got those lines.
Which is the emission spectrum.
Yeah, so that's if we've got like just that gas in there and we shoot the light through. Right?
Yep, so the other case is where we have an emission spectra. So we had to invent electricity before we could produce these emission spectra because, as it showed in that video, the idea of the emission spectra is that you give energy to the electrons, they jump up a level, and when they fall back down a level, they emit light. So the emission spectra for hydrogen looks like this, where you get light which has got a wavelength of 410 nanometers, 434, 486, and 656 nanometers. So they are the discrete energy levels that are present in the hydrogen emission spectrum, and you will see that they are also the discrete energy levels where there are gaps. And the reason why there are gaps is that when light shines, when the full spectrum shines through a hydrogen gas, then the hydrogen gas interacts with just these frequencies, or just these wavelengths, and as it showed on the video, when one of those photons hits one of the electrons, it jumps up a level, then it falls back down a level and re-emits a photon of that wavelength. But those photons of that wavelength are emitted all in random directions, so they don't go through and end up in the spectrum. So it's not completely dark. There are still some which will end up going and hitting the detector, but by far it's the vast majority of them have been removed. So this is the hydrogen emission and hydrogen absorption spectrum, and it's related to the energy levels of the electron shells, or in the electron cloud shells. So this led Bohr and his idea of the atom, and we'll talk about that in a little while. So he recognised that that emission spectrum was evidence of the quantization of the light. He also found that if you shone light at it with the only minimum frequencies of light would be produced in that emission spectrum, which is similar to the photoelectric effect, that you actually have to have specific energy levels in order for it to work. So this is what he used to generate a new model for the atom. So Rutherford had an idea about the kind of the planetary atom model, where you had stable orbits that were kind of spinning around the atom, whereas Bohr came up with the idea that there was discrete energy levels in which the electrons could exist. I think we'll look a little bit later on about how that's related to the wavelength of the particles. And the energy of each orbit is related by this equation here. So the energy level for orbit 1 would be 13.6 electron volt, or minus 13.6 electron volts. For energy level 2, it would be that divided by 4, and for 3, that divided by 9, and so on. So that allows you to work out what the energy level is for those particular, or the energy for those particular orbits.
And that's the same for every...
This is for the hydrogen atom.
Also just for hydrogen.
Sorry?
There's a different number. Instead of 13.6, it's a different number.
Yeah, so the energy levels for different atoms are different sizes. And Bohr's model of the atom is focused on hydrogen, where it's only got one electron. And it also works for a helium ion, which with a plus one charge, which again has only got one electron. When you have multiple electrons, you get interaction between the electrons, which complicates things. So, the idea, as it shows on that video, was that when you get when you get a photon of light comes through, this electron requires energy to jump up a level. It requires energy to jump up a level because it's in this orbit as a result of the electrostatic charge between the positively charged nucleus and the electron. So it needs to overcome that electrostatic charge by an input of energy in order for it to go further away, to jump away. Okay? So the energy level of each subsequent orbit is less and less because you're getting further and further away from the nucleus. And those of you who have done chemistry will be familiar with this idea as ionisation energy, which is the amount of energy required to remove an electron from a atom's outer shell.
So could it be in like the inner ring, right? First level, get hit by a photon with enough energy to move up to the next one, and then before it falls down, get hit by another photon to move up again?
Yep, jump from there to there to there to there.
Yeah, instead of like jumping from the
Yep, or jump from there up to there and then back down again. Yep. But it's less likely that that's going to occur. So the idea back here is that we're getting our photons are being absorbed, which is how we get our absorption spectra. This one here is the energy is being released, which is how we get our emission spectra, which is when we have an electron on this energy level and it drops down here. Doesn't require as much energy to stay in here, and that energy is released as a photon.
Why does it drop down?
Why does it drop down?
Stable.
Because there's a greater electrostatic attraction, so it's more stable down, further down.
So does it like when it gets the energy just go up and instantly come back again? Or is it like
Yeah, it only stays up for a very short time. Yep. And I'm not sure whether we do it or not, but they're actually in locations which is a probability distribution, which I think we do in relativity. Okay, so this shows the different levels. So we can see this base level here, which is an energy level of equal to 2, n equals 2, and it can jump up to there. That energy would be absorbed, or it can be jumping up between them. So if it goes from 6 down to 2, it's 410 nanometers. From here down to here, so you can see that the wavelength gets longer, which means the frequency decreases, which means it's emitting less energy, which you would expect because it's falling over a smaller distance, or smaller energy levels.
So good. But what if it goes from like 6 to 4?
Yeah, wouldn't that release a different wavelength?
That would release a different wavelength, yes.
So isn't there more than just 4 colours?
These are the these are the ones that are going from the excited state to the ground state.
Yeah.
So the excited state is when it absorbs energy and goes to a shell further out, and the ground state is the inside shell.
But then wouldn't there be more colours in the emission and absorption spectrum? Not
Well,
just 4.
We'll talk about those different series and the different things that they do in tomorrow's class.
Okay.
Yeah, but you need to think about it in terms of that these drop in distance here are much smaller, so much less energy is being released, so much longer wavelength, so it'll be in the infrared.
Ah,
Yeah.
yeah. Okay.
Yep. So the change in energy, so these energy levels is just HF, which is equal to the energy of the final minus the energy of the initial. So that tells you the energy level of the different shells, or the different orbitals. Okay, so let's work through an example.